In this, the final November Science podcast, PhD student Adam Rains joins me from the Australian National University to chat all things exoplanets. They're fascinating and they're redefining our understanding of planets.
Now, in its 7th year of podcasting, Trekzone presents a Trekzone conversation with your host, Matt Miller.
Well, I'm very excited to be joined by Adam Rains, who is studying exoplanets. Adam, thanks so much for your time today on Trekzone.
No problem at all. Thank you for having me.
Tell us a little bit about your research.
So I sort of work at an interesting place at the intersection between like stars and planets. And so stars and planets are formed from the same stuff. So you have a big cloud of gas and dust in space that collapses to form your stars, and the planets form around them. And so it stands to reason that by studying the stars, you can understand the planets themselves as well.
It is very cool research, and we were chatting a few weeks ago with Eloise Birchall down in Canberra, who's studying the formation of planetary systems, basically the beginnings of where your research then picks up.
Yeah, so Eloise is what we call a theoretical astronomer. So she works a lot with supercomputers, and I'm an observational astronomer. So I work with telescopes and have long nights using them, especially in the winter. But yeah, so what I do is I take spectra of the stars, or as I like to say, space rainbows. And from that, we can figure out what the stars are made of, and how hot they are and how big they are, and how that relates to any planets they might have.
It is very cool research, and something that's really only developed in the last couple of decades.
Yeah, so we didn't actually know of any exoplanets until I think it was the 90s. And since then, we've got now more than 4,000 around all sorts of different stars, around stars that are like the sun, around dead stars, around giant stars, and planets in really weird places. Like there's a kind of planet that's, imagine Jupiter in our own solar system, but if you pushed it right up close to the sun such that its year was only, a few days or a few hours, get really hot.
It's incredible, and it's redefining what we think a planet is, really, isn't it?
Yeah, so to look at our own solar system, we'd think, okay, all right, we've got our rocky planets really close to the sun. We've got some gas giants. We've got some ice giants, and there's some stuff like Pluto. But literally, this planet I just described, this hot Jupiter, that's literally what astronomers call them. That was the first planet found around a sun-like star, and wasn't what we were expecting, and it kind of turned theories of planet formation on its head. Like, how did it get there? Did it form there? Migrate there? What happened to the rest of the planets in the system? And we've since found categories of planets that aren't like what we have in the solar system as well. So there's planets that are between the size of, say, Earth and our ice giants, so Uranus or Neptune. So somewhere in between there's a boundary where you go from being mostly rocky to mostly gassy. And to look at our own solar system, we would have never known they existed, but those are actually really common planets.
And one exoplanet that Brad and I discussed a couple of weeks ago on Talkin' Science was the collision of two exoplanets in a solar system that's a billion or a couple of billion years old, sort of around the time when we were thinking that solar systems had settled down and everything was all nice and quiet in a solar system setup. But there's these exoplanets that are hitting each other.
Yeah, the universe is a pretty wild place. To give you another example, around white dwarfs, there's a group of researchers who look at the spectra of white dwarfs, and these stars have these dead stars have really pristine spectra, and they're really smooth. But if you see any aberrations in them, say from heavy elements, say stuff like iron or rocky materials, it could be that a planet, or indeed, say, comets, have fallen into the white dwarf. And so that indicates that there's still stuff going on even long after the star itself has actually, retired, so to speak.
And what are the methods of finding exoplanets? Obviously, we're familiar with the transient method and looking at the wobble of a star. But are there other ways of finding these planets and studying them?
I've sort of dealt with two of these methods. So you mentioned there's the transit method, which is essentially where you look at the planet eclipses or blocks some of the light from its star. So the planet has to be lined up from our perspective here on Earth. And it will block a bit of the light, and a year later, from the perspective of that planet, it will pass in front of its star again and block the light. And so for a big planet, it could block a percentage of the light. It could block 8% of the light. Or for a really small planet, it could not block very much at all. And NASA's got a mission that launched launched last year that's looked at, many thousands of planets and come up with some candidates for these transiting exoplanets. But the thing is, that gives you the size of the planet. So you might know you've got a percentage drop in the amount of light, but that means something very different if you've got a giant star or a giant planet or a small star. So to figure out how big the planet is in terms of its mass, you've got to do the wobble method, the radial velocity technique, which is where you use my favorite technique, space rainbows, spectra. On a telescope, you split the light into a rainbow and you watch as all the elemental absorption features. This is where you've got atoms and molecules absorbing light in the star. The planet and the star actually go around their common center of mass, so the star is coming towards you or away from you at certain times. And with the sensitive enough telescope, you can actually detect this. And you get a wobble, like a period that matches up with the dips in light you can see. And by combining these two techniques, you can find the size of your planet and the mass of it and then get its density, which then lets you say, oh, this is definitely a rocky planet, or maybe this is like a water world or a gas giant. And those two techniques really give us a lot of information.
And we're finding all these sorts of different planets out there. I know you mentioned just before that it's essentially redefining what we think of planets, water worlds and big rocky planets, all sorts of crazy things. Has there been a favourite exoplanet of yours that's been discovered?
One of the ones I like to come back to, it's had a lot of research. It's the TRAPPIST-1 system, because it was a system around a red dwarf star. So this is a star that is very close to not even being a star, because if you don't have enough mass, you can't burn hydrogen into helium. So it's something like 2,000 odd degrees Kelvin, and it's probably like less than 10% the mass of the sun, the size of the sun, and it's got 7 planets around it.
Wow.
7 rocky planets, and all of these planets, I think, are inside the orbit of Mercury.
Oh, wow.
So they have really short periods. Some of them would be and there's been questions like, these stars are really different from the sun. Where is their habitable zone? These stars flare a lot. They have like a lot of solar, well, not solar, but stellar flares where they increase in brightness. And, maybe that's bad for life. Maybe it could torch the surface of a planet. And so there's a lot of studies been done into, the habitable zones of different planets around different kinds of stars.
Well, Adam, I do have to ask very quickly whether you, let's say interstellar travel is possible within a lifetime. Would you visit an exoplanet?
If it was safe to do, safe to do so, absolutely. I mean, there's some things, so imagine how they'd be up close, or even planets that we haven't even dreamed of before.
Absolutely incredible, Adam. Well, it has been fascinating to take a bite-sized look at exoplanets with you, and it's a field where exoplanets are being discovered almost every other week, which is absolutely incredible. Yeah,
we're making great strides, and there's lots of researchers all around the world, but Australia's doing its fair share too. We've got 4-meter telescope at Siding Spring Observatory, which is in the middle of nowhere in New South Wales, really dark skies. And it's got one of the most sensitive instruments on the planet for hunting for these planets now. As an astronomer, though, do you wish that you could observe things during the day to not break your sleep pattern? Some astronomers can. If you're a radio astronomer, like, the sky isn't bright in radio light, so if you're a radio astronomer, you can observe during the day. Or I could just use telescopes on the other side of the planet, which I do occasionally as well. So it's the handy thing about having such a large planet and having two sides always facing opposite directions of the sun, isn't it? It is, yeah. And gone are the days where, it's astronomers are cloistered away on a mountain, away from anything, just, manually turning a crank handle to operate their telescope. It's all much more electronic and interconnected, and get a lot more science done this way. What a world we live in, hey, Adam? Very much so. Fantastic. Well, Adam, I really appreciate your time, and good luck finding some more exoplanets. Thank you very much.